Mhm. All right. So welcome all to the latest FSML seminar. And today it's my great pleasure to introduce Professor Ashwin Renganathan for today's talk. He's an assistant professor of aerospace engineering at Penn State and holds a joint appointment with the Penn State Institute of Computational and Data Sciences. He directs the Computational Complex Engineered Systems Design Laboratory or CSDL at Penn State. He's broadly interested in developing novel and scalable computational techniques for surrogate modeling, uncertainty quantification, and numerical optimization, with a focus on aerospace applications. He earned his PhD in aerospace engineering from Georgia Tech and previously completed a postdoctoral appointment in applied mathematics at Argonne National Laboratory. We are very pleased to have you with us today for this talk, and please feel free to take it away. Yeah.
All right. Thanks, Aniket. Thanks for the kind invitation. And also, thanks for organizing such a thoughtful seminar series. So the way I've designed my talk for today is it could be unconventional for this series, but what I've done is I've given um, the first few slides to provide an overview of what research we do, because I couldn't predict who would be in the audience or who would eventually see the video on YouTube. And then I deep dive into one of our recent work, which might be of interest to this audience as well. So yeah, hopefully that works out well, and hopefully it's not too busy, but we'll see. All right, so the outline is pretty straightforward, so I'll just cut to the chase. My group, like Aniket just said, is titled Computational Complex Engineered Systems Design Lab, CSDL for short. And what we do in my group is develop scalable computational techniques toward the design of complex engineered systems. So a complex engineered system can be thought of as any engineered system which has a non-trivial cost of prototyping and testing, right? Which means, if you're trying to find the best design, you can't just brute force your way through trying out different arbitrary designs. You have to be judicious about, the cost involved. And so mathematically speaking, we treat the complex system as a black box, and a sophisticated term for that is a zeroth order expensive oracle. Zeroth order essentially means there is no derivative information available. Usually, derivative information is a luxury in analysis and design. And crucially, this is expensive, right? So which means the methods we develop has to minimize the number of queries we make to this expensive oracle. So we have control over inputs that go into this oracle, and then we can observe output y. And this functional form f of x is something that is unknown to us, right? So that's why it's a black box or an oracle. So what do we want to do with this? We want to do design. And what do we mean by design? There could be several interpretations to it. But what we mean is essentially decision making, right? So we are interested in the mathematics of computational decision making, which focuses on three pivotal areas, including surrogate modeling, which you can think of as supervised machine learning, for instance. Um, and UQ is to handle uncertainty of any form, maybe propagate them or sometimes quantify uncertainty existing in the system. And then the final destination of decision making is usually optimization or control, where you're trying to find an optimal design or an optimal decision, given some objectives and constraints, right? So these three by themselves are pretty broad fields in applied mathematics and engineering, right? But they also are highly interconnected and they overlap. For instance, optimization might involve surrogate modeling, for example, in trust region methods. Surrogate modeling might need optimization to estimate hyperparameters. UQ is required in stochastic optimization, so on and so forth, right? So we coined a name for these three areas and we call it decision-making triad. And pretty much all of the work that we've done so far and what we plan to do for the next 5 to 10 years in my group would address different aspects of the decision-making triad. All right. So I realize that this seminar series is also motivated by AI for science. And I'm pretty sure some of you in the audience at least would recognize that this term was coined by the Department of Energy in 2019. And in fact, I was when I was a postdoc at Argonne, this happened just a few meters away from my desk, the town hall meeting that kind of put together these ideas. So this is a chart straight from the basic research needs for AI for Science report. And two of the main three areas they identify are machine learning enhanced modeling and simulation. So this is essentially surrogate modeling of different forms. And then intelligent automation and decision support, which would be, like decision making, such as optimization and control, for instance, right? So our focus addresses two primary areas within the, basic research need topics identified in this town hall meeting. And then related to the same thing, there was a AI for Science report that came out the very next year. And in that, they identify some key areas to focus on that requires advances for AI in the next decade. And lo and behold, they identify surrogate modeling, numerical optimization, and UQ as three important areas, right? So the three areas, like I said, they often appear together, and they are extremely important in computational design. All right. So having said that, we are engineers working in an engineering department. So we're also interested in AI for engineering, right? And specifically in aerospace engineering, one application that motivates our work is certification by analysis. So if there are any non-aerospace engineers, you might not be familiar with this, but any commercial airplane that uses the U.S. airspace has to be certified by the Federal Aviation Administration for airworthiness, right? So this certification process involves testing the aircraft at extreme conditions. For instance, at high angles of attack, or taking off and landing at side wind, crosswind conditions, and so on. So this process of certification is time consuming. So typically it takes about 3 to 5 years due to scheduling delays and whatnot. And they're also expensive. So the 2021 report identified approximately $100 million for the FAA to do certification each year. And sometimes they could even be unreliable, right? Because you have to wait for the right weather conditions and stuff like that. So CBA was introduced in the early part of this decade. And the goal there is to cut flight tests by 50% for certification. Um, and they want to do that by replacing some of the actual flight tests with, computational analysis, right? In other words, you want to use computational simulations to do some of these tests, but the reliability of those simulations cannot happen without rigorous uncertainty quantification, right? So rigorous UQ and some of the decision-making methods that we are working on are critical to, enable this. But the challenge, though, is that, like I said in the beginning, these models are expensive to evaluate, right? So some of the aerodynamic model of aircraft that we do takes, upwards of 2,000 CPU hours for one query, right? So evaluating it more than a few dozen times is not practical. So the challenge really is, how do you make decisions for these complex systems with as few queries to these high fidelity models as possible, right? So that's an important challenge that needs to be addressed. So along the same lines, the NASA CFD Vision 2030 is another important motivation for our work. I know 2030 is almost here, but NASA recently extended this to CFD Vision 2040. The report is, I think it'll be out very soon. I know this chart is pretty busy, but the idea here is that uh, NASA is interested in, making advances to CFD such that other aspects of aircraft design is kind of blended into the CFD framework, right? So one thing that we are interested in is enabling uncertainty quantification for multidisciplinary analysis and optimization, where you can have, more than one discipline interacting, everything in high fidelity, and also appropriately quantify the uncertainties that go with these model predictions in also designing the aircraft. Okay, so these are so in summary, AI for science and AI for engineering are driving forces behind the kind of research we do. And broadly, our research typically involves three critical steps, right? So usually we identify a problem, and then we come up with the necessary theory to solve that problem. And then we formulate a methodology based on that theory, and then we also implement software that we publish as open source, right? And which is also becoming very common these days. Um, so with this workflow, we have the following goals or objectives that we try to meet in all the methods we develop. The first one is sample efficiency. So you will see me repeating this term sample efficiency frequently throughout this presentation. What it means is you want to minimize the number of queries to the expensive model, right? And you want to find an answer to your question with as few queries as possible. Our methods are derivative free. Like I said, derivatives are usually, they are a luxury in practical applications. So we want to adapt to the lack of derivative information. We want to make it scalable to high dimensions, and also, when possible, we want to show some theoretical guarantees. All right. So before I kind of delve into the technical aspects of my talk, I want to quickly, I want to set up the audience because, I'm not really familiar with this audience. I want to set you up to know what to expect out of this talk, right? So this talk is about AI ML for decision making, okay, which includes AI for science and engineering, as I established previously. So specifically, we are interested in solving the outer loop of things, right? So where we wrap around a PDE system which might be expensive to evaluate, and then we're trying to solve some decision-making problem. And we are interested in adaptive techniques that keeps the number of queries to the PDE minimal. Um, and we want to be able to accommodate uncertainty in a seamless fashion. And we also want the methods to be agnostic to underlying physics of the system, right? So in a sense, it's somewhat antithetical to physics-informed machine learning. We are interested more in the physics agnostic machine learning and decision making using machine learning, right? So in that sense, we're not interested in solving PDEs with AI or ML. And this talk will have no neural networks, nothing against neural networks. It's just that we have very specific requirements, and the type of methods that we choose seem to be more suited for those requirements. So what is our method? Broadly speaking, it's kernel methods with Bayesian decision theory. So I'm going to, give a brief introduction to what I mean by kernel methods and Bayesian decision theory. And I hope there are no questions so far. Okay. So, um, like I said, our methods fall under the broad category of kernel methods. What they mean is that they're a class of methods where the some data X, in this case, X is just your input, right? It's transformed into a higher dimensional feature space, phi of X, for better expressibility. So the reason you want to lift your input to a higher dimensional space is because sometimes it exposes some hidden structure. Sometimes it eases analysis. For instance, if you're trying to do classification, linear separability might not be achievable in the original space, but in the higher dimensional feature space, it could be achievable. And therefore, it makes classification easy, right? So kernel methods typically involve a kernel function, K, which can be thought of as a similarity function that captures the similarity over pairs of data points, X and X prime, all over the domain, right? So this similarity is expressed as an inner product involving a weight matrix sigma, okay? Um, so in principle, you have to compute this inner product to, compute this kernel function, and then the kernel function is used in different forms to, for example, come up with an approximation to your unknown function f of x, with which you can do, other stuff like UQ optimization and so on. But fortunately, in practice, you don't have to necessarily compute this inner product manually. You can use something called the kernel trick, where you can directly specify a functional form for this kernel. And this is enabled by something called the representer theorem. And I don't think I want to go into the details, but essentially, you can directly specify a functional form for this kernel, and then you can use it for whatever purpose you're trying to do, right? So our methods fall under this kernel method category. And we specifically focus on Gaussian process models, which is just one type of kernel method. And I'm pretty sure, many of you have heard of Gaussian process models. So here's a very, quick and brief overview. So the idea here is our unknown function f of x, like I said, has no known structure, and it's also expensive. So we approximate that using some surrogate y, and we place a prior distribution over this surrogate model, which is a Gaussian process, parameterized by some mean and a kernel k. right? And the kernel K is parameterized by some hyperparameters omega, which can be estimated in a variety of forms, right? So, for instance, I could specify the mean to be 0 for the lack of any specific information, and the kernel can be chosen as this squared exponential form, which has a hyperparameter Lx squared. The Lx is a length scale that determines how fast or how slow the function you think varies, right? So we don't know anything about the function, so we make an assumption. And this particular assumption leads to functions that look like these draws. So what you see in this figure are random draws extracted from this prior distribution, right? So you can encode more information into this prior assumption. For example, if you know that your unknown function is likely to take, likely to go through sharp changes, you can encode that information, and then these draws will look different, right? So essentially what we're saying is we assign a distribution over the function space, and then we say our unknown function is best approximated by some draw from this whole distribution, right? So you don't have to necessarily search for that draw that best approximates your unknown function. Fortunately, there is theory that makes this process easier. And you do that by first making some finite number of observations on the unknown function. Those are shown by these black circles, right? So once you have these observations, you have more information about your function. You also have a prior assumption. You can combine these two using Bayes' law, right? And if your likelihood in Bayes' law is also Gaussian, you get a Gaussian process posterior distribution that looks like what you see here, right? So essentially, this is a process of eliminating all the draws that did not pass through these observations. Because once you made these observations, you know that your function, your distribution, all the draws from a distribution has to necessarily pass through these points, right? So now you have a more updated probabilistic prediction of what your function looks like, right? And here I'm just showing a finite number of draws from the surrogate model, but essentially you can construct confidence bands, and you can have an expected value for the surrogate model that you can use for any downstream purposes. Was there a question or something?
No, I don't think so.
Okay. All right. So that was Gaussian process. I'm pretty sure several of you have probably, even used it to good measure. We also work with deep Gaussian process models, which I mean, I mentioned that there's no neural networks here, but here's an idea drawn from neural networks where you can take a Gaussian process and compose it into another Gaussian process, and you can do it in a neural network-like fashion, right? So on the top, you have a regular Gaussian process which maps your input X to output Y. You can map your input X to some latent node Z, and then you can map the Z to the output Y using another Gaussian process, right? So Z is conditionally Gaussian on X, and then Y is conditionally Gaussian on Z. So this would be a one-layer deep Gaussian process, right? So you can add the number of layers. So here's an example of a three-layer deep Gaussian process. And you can also have multiple nodes per layer, just like what you do in neural networks, right? So why do we do this? Because this allows you to add more expressibility in your model predictions, right? And I'll show you one example in the next slide. But this greater flexibility in predictions comes with an additional cost of model inference, right? So now inferring these parameters will incur an additional cost, but we've done some work. I'll show you some citations of our past work where you can still do Bayesian inference on these models. In in quasi real time without taking too much, and we can still solve decision making problems with them. Okay, so here's an example of why you would need a deep Gaussian process. So let's say your true function is a step function. So it's non-differentiable because it goes through the step right here, right? If you were to use a regular GP with the kernel very similar to what I showed you a few slides ago, it's going to come up with a prediction that tries to over smooth the original function, right? So in fact, unless you create a dense set of samples in the original function, excuse me, you're never going to be able to recover this true step function, right? On the other hand, with the same set of observations, a deep Gaussian process with two layers gives you a much closer approximation to the step function, right? So this phenomenon is called non-stationarity in statistics. It means that the rate of change of your function changes with your input location. So the rate of change of the function in this region is practically zero, but suddenly it goes through a change here, and then again it becomes zero, right? So such functions are called non-stationary, and deep Gaussian processes are very good at capturing this non-stationarity, of course, at an additional cost, right? And we found in a lot of our past work that non-stationarity is a real thing. It does occur in a lot of real-world applications. So we need so deep GPs really help out in such complex situations where regular GPs cannot help much. Okay, so that covers how we develop our surrogate models using our choice of kernel methods. What we do with it is we don't want to commit a budget of training data to fit these models a priori, right? Because like I said, our unknown function is expensive to evaluate, so we want to make it adaptive. And what allows us to be adaptive in fitting these circuit models is Bayesian decision theory, right? So let's say you have some function u that operates on this unknown function f that can quantify the utility of evaluating a candidate input on F, right? Um, so so if you have to really evaluate the true function to find out if a candidate input is, valuable or not. Because what we're trying to do here is even before we evaluate the true function, we are trying to find the most useful candidate points in the input domain, right? And it defeats the purpose if we have to go and evaluate the true function to find out it's the utility of the candidate itself, right? So the natural way to circumvent this in computational statistics is to replace it with a surrogate estimate y, right? So now this utility function becomes stochastic, right? So you can choose your new observation in a greedy fashion by maximizing the expected utility given all the previously observed data, right? So we take the expectation because this u is stochastic and the expectation is with respect to the surrogate model itself, right? So then we can choose the new observation site, make an observation at that location, and then we can repeat this. So this whole right-hand side is commonly denoted as alpha, and it's called the acquisition function. And this acquisition function can be customized according to your application. So whatever you're trying to do, it could be optimization, it could be UQ, it could be, something completely different. And you can customize it to kind of greedily, maximize the amount of information you gather from all the evaluations you make on the unknown function f. Okay, so just a quick example. Let's say your goal is to maximize some function f of x and find one of its global maximizers, right? What you do is you start by fitting a Gaussian process on a finite set of observations on this function. Let's say, lowercase n observations. And let's denote the best observed function value. So that is the highest function value that you observed among the n observations you made as f plus, right? So a popular utility function is specified as this, right? The max of u, max of 0, and the difference between your surrogate estimate and this f plus. Okay, so essentially you're trying to quantify the improvement that you can gain over the best observed value. And this stochastic quantity, if you take its expectation with respect to the posterior Gaussian process, you actually get a closed form expression, as you see on the right. And if you notice this right-hand side, it depends only on the posterior mean and the standard deviation of your Gaussian process. And the little phi and the uppercase phi are the standard normal PDF and CDF respectively, not to be confused with the basis functions that we previously saw, right? So this acquisition function is the well-known expected improvement. And what you do is you choose your next point by maximizing this acquisition function, make a new observation, update your Gaussian process, and repeat this process. And this is usually continued until you exhaust your budget of evaluations, right? So this is kind of like the boilerplate Bayesian sequential experiment design. And this is also popularly known as Bayesian optimization, because this is usually the common application of doing this is to optimize some unknown function, right? But like I said, it doesn't have to necessarily be to optimize a function. And we've done work for other applications as well. Some of our past work involve just developing adaptive surrogate models for aerodynamics. More recently, we've been working on a problem called contour finding, which is related to reliability analysis for complex systems. So finding the failure contours and estimating failure probabilities can also be done efficiently with kernel methods and this Bayesian sequential experiment design, right? So these are just citations for anybody that might be interested. These acquisition functions, people have been developing this for decades now, and even new acquisition functions keep getting introduced as we speak. And there are really a zoo of acquisition functions, but I'm just highlighting Thomson sampling because it's connected to what I'm going to talk about for the rest of this presentation. Okay, um, so a quick primer on Thomson sampling. Um, Thomson sampling is not a new idea at all. It has existed since the 1930s. And the idea is inspired from the so-called multi-arm bandit problem. So you have a set of slot machines which has an arm. You pay some money to play, you pull its arm, and then sometimes you win a reward, but most of the times you don't. It's called a bandit because it takes money from you, and most of the times it keeps it and makes you pay more, and very rarely it gives you a reward, right? So each of these slot machines have a certain unknown probability of giving you a reward. If you were to pull these slot machines the finite number of times, one way to maximize your profit is to use Thompson sampling, right? So what you can do is you can randomly start pulling these slot machines, and then after every draw, you can try to learn exactly how the probability of success is distributed, and then you can exploit that knowledge to maximize your profit. And sometimes you can also explore just to randomly draw the slot machines, but eventually you can exploit to, like I said, maximize your profit, right? So the idea behind Thomson sampling is to make decisions according to the probability that they are optimal, right? So in the context of Bayesian sequential experiment design and optimization, what this means is you make new observations at points which are defined according to some distribution P sub x star of x, where this is the probability density of the maximizers of your unknown expensive function f, right? In other words, if you know how the maximizers of a given function are distributed, then you just sample from that. And again, it defeats the purpose to find that distribution by evaluating your f because f is expensive. So what we can do in the context of Bayesian optimization is construct this density using this formula here, right? So the delta here is the Dirac delta function. So what you can do is you can put all the mass of this density at a maximizer of a posterior draw from your Gaussian process model, right? And then integrate this out using the posterior, right? So in practice, you don't necessarily have to construct this density either. What we do is we construct a Gaussian process model, sample from its posterior, and then find its maximizer, and then use that as the next location where you want to make an observation, and then you repeat this process, right? And theoretically, it can be shown that this process is consistent, eventually recovering the true density, but also it naturally balances exploration and exploitation. Okay, so what I had a quick demonstration of how this works. So here is a true uh, a function which is called the Ackley function, shown in the dashed lines. It is just shown for reference. In practice, we never know what the function looks like. And we're trying to find its global minimizer, which is right here at the center, right? We start off with just one observation of this function, which is the blue circle here. And since we don't have any other information, the Gaussian process model essentially is flat because we don't have more than one observation. And a draw from this Gaussian process is also flat, excuse me, right? So what we do is we have to find the maximizer of this red curve to place the next observation. And since it's flat, it's essentially choosing a random point from your input domain. And that's what happens at the next step. A random point is chosen, right? And now you can update your surrogate model. And now you have something that has some curvature. So the shaded region are the 95% confidence intervals of your, surrogate model. And then the red line is just one random draw, and it's just a 95% confidence interval, right? So a draw can be outside of this interval, and that's what is happening here. So what you do is you choose the minimizer of this red curve here, right? And that happens to be towards the end of this domain. So what you have is a new observation at this end, and then you keep repeating this process a few times, right? What happens is it explores the design space and tries to learn this curve reasonably well. And then it starts exploiting this location by putting more and more points there. And then occasionally it again, starts, exploring as necessary, right? So in this case, within just a few iterations, it was able to recover this global minimizer. But while doing so, it also tried to explore the design space, right? So Thomson sampling is a very powerful tool. And what I'm going to talk about in the remainder of this presentation is how you can take this Thomson sampling for single objective optimization to optimize multiple objectives at the same time. So we want to look at extensions to multi-objective optimization, which has even broader applications than, just plainly single objective optimization. Okay. All right. So that's where we're headed next. So we are interested in solving a constrained multi-objective optimization problem where we have a bunch of k objectives, right? So these k objectives have could have some sort of a conflict between each other. For instance, the maximizer of F1 doesn't have to be necessarily the maximizer of F2 and so on, right? In fact, it could be exactly the opposite. The maximizer of F1 could be close to a minimizer of F2. So you have this conflict between these different objectives. So independently maximizing each of these objectives is, not what you want, right? So you want to find a pragmatic compromise between all of these k objectives that gives you some sort of an optimal solution. And I'll formally define what I mean by an optimal solution in this context, right? And additionally, it could have constraints, which could also be zeroth order oracles, right? So here, the calligraphic E is the set of indices that correspond to equality constraints, and the calligraphic I are the set of indices that correspond to inequality constraints. And we want to solve this in a sample efficient manner, so minimize the number of queries to all of these functions. And we also want to provide some sort of a theoretical guarantee that the method will, converge to the true answer, right? So that's what we are trying to achieve. So why should we care about multi-objective optimization? Well, it finds widespread application. I'm just scraping the surface of all its applications, but just within aerospace, supersonic aircraft is a very good application where, in addition to minimizing the drag of the aircraft, you also have to care about sonic boom, right? And sometimes these can be conflicting, right? So you have to look at two objectives at the same time. In subsonic aircraft, there could be multiple cruise points that we might have to simultaneously consider, and I'll be showing an example on this. Automobiles are frequently designed for maximal safety, minimal weight, sometimes trying to minimize the impact of one particular accident, and so on and so forth. Machine learning is usually, the goal is to find the minimalistic architecture, if you're familiar with Occam's razor, while also minimizing the validation error and so on. But the list keeps going on, right? And the solution to all of this is multi-objective optimization. And we found out that the existing work in multi-objective optimization had so many limitations that we try to overcome in this work. Okay, so what does it mean to solve the multi-objective optimization problem that we previously saw? In single objective optimization, we all know that the first order necessary conditions are the KKT conditions, right? In the multi-objective context, Pareto optimality is the necessary condition that you need to solve for. So just a very brief primer to what Pareto optimality means. So if you were to aggregate all the k objectives into a vector, call it boldface F, and call that a solution, then that solution Pareto dominates another solution f of x prime if f sub k of x is greater than or equal to f sub k of x prime, where x and x prime are any points in the domain. And this has to be true for all the objectives. And there exists at least one objective k where this inequality is strict. Okay, so that's the definition of Pareto optimality. So this is what we're trying to find. We're trying to find that X that will satisfy this condition. And while we do so, the set of all objectives that satisfies this condition is called the Pareto frontier. And the set of all inputs that correspond to the Pareto frontier is the Pareto set. So the Pareto set is denoted as calligraphic X star, and then the frontier is denoted calligraphic Y star, right? Okay, in practice, finding this Pareto set and Pareto frontier doesn't have to be, through some sort of a comparison between different pairs of points to see if this condition is satisfied. We can look at something called the hypervolume, right? And I'll illustrate hypervolume in the next slide, but the hypervolume indicator is used to measure Pareto optimality. So usually if we monitor this indicator, it's usually a good measure of, whether the algorithm is converging or not. So here's a very simple illustration with just two objectives, right? So I have two objectives, F1 and F2. And the blue circles that you see are just a scatter plot of these objectives evaluated at a random set of inputs X. Okay, that's the blue. And then the red star is just a reference point, which corresponds to the absolute worst if you were to minimize each of these objectives independently. Okay. And then the orange identifies a subset of these blue circles that are Pareto optimal for this set. Okay. And then the hypervolume is essentially the region enclosed between the orange circles and this red star. Okay. So that's the hypervolume. Now, notice that the orange circles are placed such that no other blue circle has a better value. So we're trying to maximize two objectives, right? So a better value would be a higher value in F1 and a higher value in F2. So no other blue circle has a better value than these orange circles in terms of both objectives. Sometimes it can happen with respect to one of the two objectives, but not both, right? So that's why these orange points are non-dominated, and this indicate the shaded region is the hypervolume. But now, if you were to find a point that dominates these orange circles, it would look like this red circle on the right. Okay. So if there is another point that dominates any of these orange circles, then the hypervolume increases as shown by the red region on the right. Okay. So what I'm trying to say is this hypervolume is a monotonic increasing measure that we can monitor as the algorithm progresses. And once the true Pareto frontier is identified, this hypervolume stops decreasing. So it starts plateauing out. So it's a very good way of determining if your algorithm converge or not. Okay. So how do we solve these problems, the multi-objective constraint problems that I mentioned? The de facto method in the community is to use genetic algorithms, right? So non-dominated sorting genetic algorithm, or NSGA, is very popular. So this particular paper, I believe, has hundreds of thousands of citations already. NSGA is very popular. It's very accurate, but it's computationally very expensive because if anybody is familiar with genetic algorithms, it depends on creating a dense population of candidates and then trying to filter them out based on some fitness function and then kind of repeating this process, right? Usually we cannot afford that level of computation in our applications, right? It's just not feasible to do so. But these algorithms are the most accurate known so far, at least what we are familiar with. On the other hand, Bayesian optimization can also be applied to multi-objective optimization, except most of the work in multi-objective Bayesian optimization is less accurate, although it's highly sample efficient. Okay. So what we wanted to do is somehow combine these two ideas and get the best of both worlds. So we wanted something that is sample efficient while also being accurate. Okay, so that's kind of the high level goal of what we are trying to do with this particular work. So, a very, high level review of what has been done in multi-objective Bayesian optimization. We identified three categorizations for all the existing work. So the first category is to use something called a scalarization, right? So you have K objectives. You can use some weights and scalarize these K objectives into a scalar, right? And then you can use single objective optimization techniques to optimize that. But the problem there is, how do you choose these weights and how many such weights do you choose? I think that's a very important question. And sometimes it could just not be tractable for a lot of problems, right? And also, if the Pareto frontier is somewhat, complicated with disjoint regions and so on, these methods are known not to work that great. The other class of methods are hypervolume based. So I just showed you what a hypervolume is. So methods actually computes this hypervolume, um, and try to find candidates that will give you the best improvement over this hypervolume, for instance, or trying to quantify some sort of an entropy of this hypervolume. The problem with hypervolume is that it's not that easy to compute. So let me back up real quick. So computing this area is not that straightforward, particularly if you have more than two objectives, right? So it doesn't scale well with the number of objectives, and usually what we come up with is a good approximation to this area or volume in higher dimensions. And trying to devise methods that depend on this computation is usually not that efficient, right? And then the third class of methods are entropy based, which computes the information entropy of some quantity. It could involve hypervolume. It could involve other characteristics. The problem with entropy is that usually it's not available in closed form. So you have to use some sort of a Monte Carlo sampling, for instance, or maybe approximation techniques to make this method tractable. So we identified that most of the existing work, they had this hard, non-convex, and occasionally stochastic acquisition function that you have to still optimize. And the whole point of Bayesian optimization is to, kind of optimize functions without much knowledge of its structure or anything. But if that leads you to optimizing another hard acquisition function, it kind of becomes a rabbit hole, right? And most of the methods also are unable to handle constraints and noisy objectives and even batch acquisition. So our overall method that I'm going to talk about overcomes all these limitations. Okay, so we came up with a new method that is called Pareto optimal Thompson sampling, or qPOTS. Q stands for batch sampling, and it'll become clear in a couple of slides. So this work was recently published in AI Stats, and the idea here is to take the Thompson sampling idea that we just saw a few slides ago and extend it to the multi-objective setting that so far nobody had done. So the idea is, if you remember that density that I showed you a few slides ago, this density looks very similar, except in this inner Dirac delta function, we have a multi-objective optimization problem that involves a multi-objective optimization over k objectives, except these k objectives are represented by their surrogate models, Y as opposed to the F, right? So we have an inner multi-objective optimization problem over the surrogates. And since we have k objectives, we have to integrate this Dirac delta function over with the k posterior GPs, right? So again, this is a very unwieldy integral, but we never have to evaluate this integral. In practice, what we can do is we can draw samples, posterior samples from the Gaussian process model, and then solve this inner multi-objective optimization problem over those posterior samples, and then we can proceed as usual. And I'll give you an illustration real quick. So we start off by, for simplicity, I'm assuming there are no constraints, but I'll show you how to add constraints. You start off by fitting KGP models. So you just sample your objective functions, and using that data, you fit models. And then once you have KGP posterior models, you draw KGP posterior sample paths, right? You can use the so-called reparameterization trick, right? So the Z here is a standard normal random variable. And then the mu is the posterior mean of the Gaussian process. And then the sigma is the posterior covariance, right? So you just have to compute the square root of this covariance, multiply that by the standard normal, add the mean, and you get a GP posterior sample path, right? So this square root can become unwieldy in higher dimensions, but we propose some measures to take care of that. But anyway, you draw k posterior sample paths, right? And then what you do is you solve a cheap multi-objective optimization problem using the k posterior sample paths, except now you use evolutionary approaches like NSGA, right? So when I said we're trying to get the best of both worlds, what I meant is we still use genetic algorithm, except we use that on the surrogate models, which are a lot cheaper to evaluate as opposed to using them on the true function, right? So this gives us a random Pareto set, X star, and then we choose a point from this random Pareto frontier. Okay. And then we can make a new observation at this new point and then update the Gaussian processes for all the k objectives, and then we can repeat this process. Except even though we can choose any point from that random Pareto set, X star, we figured there is probably a more clever way of doing that, which is you choose that point which tries to maximize the minimum distance to all the previously observed sites, right? So it's called a maximum problem. So we define the Euclidean distance gamma as the distance between any 2 points x and x prime. So we compute the Euclidean distance between any point on the Pareto set x star, and then any point on the previously observed sites xi. And then we try to find this minimum distance, and we try to find the maximizer of this minimum distance. And I'll show you a graphical illustration of this. But maximum problems are pretty common in optimization and statistics. But the key thing here is we can do an acquisition of q points in a batch to evaluate them in a parallel high performance computing environment, right? So we can do that in a sequential fashion. So we can draw the n+1th point by finding the maximum point using the previously observed endpoints. Once we find that point, we can append that to the existing observed sites, solve this maximum problem again, get the n+2th point, and repeat this until we have a batch of q points, right? And if anybody's concerned about, how do you solve this maximum problem because it looks expensive, it is actually not. And I'm happy to discuss that offline if anybody has a question. Okay, so how does it work in practice? So here is a two-dimensional function. And what you see here are the representation in the output space on the left and input space on the right. The brown circles are the observations that you made on the Gaussian process, right? So it's easy to see that on the right, where these brown circles are somewhat uniformly distributed. That's where you make observations and you fit your Gaussian process models. And the blue circles are the random Pareto frontier computed using just the surrogate model. And then the black symbols are the true Pareto frontier that you don't know, but it's just shown for, reference, right? And then the same is shown in the input space. And then the blue circle is the acquisition we make out of all the blue circles. The blue square is the final acquisition that the method makes. So notice what it does. It's hard to, eyeball it, but it essentially chooses that blue circle that has the largest minimum distance to all the brown circles. Okay. So in this case, it tries to exploit its knowledge of the true Pareto set. And then with more observations, notice how this blue Pareto frontier is approaching the true Pareto frontier, right? So now the acquisition through our method chooses something that is far away, so it explores. And then with even more points, it starts exploiting. And the random Pareto frontier converges to the true Pareto frontier, and we continue to exploit, right? So this also demonstrates an asymptotic convergence of our method, which we also theoretically prove later. If you have constraints, okay, I'll try to wrap up in about 5 minutes. So if you have constraints, the process is very similar, except now you have, let's say you have C additional constraints, right? And then you fit C additional Gaussian process models for all of the constraints. And you just take the same integral that you previously saw and add a couple of indicator functions that filters out the points according to the feasibility of these constraints. So the key thing here is that the feasibility is measured using the surrogate model, not the true function. And therefore, sometimes you might have infeasible points, which is fine, but it's still useful because it can be used to enhance the surrogate model, right? And here's a demo of how it works in the constraint setting. So we have the same, two objective random QRN function, but now we have a constraint, and then the symbols are the same. The blue is the random Pareto frontier, black is the truth, and then the blue square on the right is the new acquisition. So notice it chooses that point which still has the largest minimum distance to the brown circles, right? So it seamlessly handles constraint problems. We prove a theorem that guarantees that under some mild assumptions, the predicted Pareto frontier using our surrogate will converge to the true Pareto frontier, but that's not super important. We just show that it's asymptotically consistent. But what I want to wrap up with is showing an aircraft application. So we are interested in long haul and even medium haul subsonic aircraft design optimization. And if you look at what happens for an aircraft in cruise condition, usually the properties, the operating conditions are not constant, right? So the required lift is constantly decreasing because the weight of the aircraft is decreasing. This requires, change in the lift and therefore change in thrust, which changes the Mach number and the Reynolds number if you're trying to cruise. So there are so many changes that happens even during the cruise condition. So ideally, you want to consider all these changing conditions in designing your aircraft wing, right? So we want to simultaneously consider multiple points, and that's what we do. We consider two operating conditions at two different Mach numbers and angle of attack, and we try to minimize the drag at these two conditions. So we use the high-speed NASA Common Research Model, which the aerodynamics is taken care of by the SU2 multiphysics code. We use something called a free-form deformation to parameterize the wing. So we're trying to find the optimal wing shape by considering two objectives, which is the drag at two different operating conditions. So we parameterize it using what's called an FFT box. And the circles that you see in these boxes are called control points. You can move these control points upward and downward, which would morph the shape of this wing. And that can be passed into an optimizer for it to find the optimal shape. So when we did that, this is what the Pareto plot looked like. So we have the drag at the two cruise points, and the blue circles are all the designs that the algorithm evaluated. And notice that in part of the design space, the two objectives are actually correlated with each other, which means minimizing one objective actually minimizes the other, and vice versa. But that's not true everywhere, right? So there are other parts of the design space where you could achieve a very low drag for cruise point one, but it could lead to a higher drag for cruise point two and vice versa. So the Pareto optimal points are these red circles that you see here. Naturally, most of them are accumulated towards this corner, but you can also have sometimes Pareto optimal solutions like this red point over here, which has the least drag for cruise point two, at the cost of slightly higher drag for cruise point one. And sometimes this might be necessary for a practitioner because maybe cruise point two is more important than cruise point one. All right. In such cases, this design could actually be more valuable than any of these other red designs, right? So I'll quickly show what the pressure distribution on the wing looks like. So on the left, you have a baseline design where you have the strong shock towards the trailing edge. The optimization, displaces the shock, but not just displacing it, it also weakens the shock significantly, resulting in a significant reduction in the drag in the cruise point one, and the cruise point two is practically the same. Um, um, so the key idea here is that if you were to just look at a single objective, optimization tries to completely eliminate this shock and try to decrease the drag, but the same design at a different operating condition might be completely non-optimal, right? So the multi-objective optimization problem gives you a pragmatic compromise where a shock might still exist, but this gives you the least possible drag in all, all conditions considered combined, right? So I just have multiple examples of this. So I'll quickly skim through this. But here's an example of cross-section of the wing at different stations. So the red is optimized and the blue is the undeformed baseline. And notice that the optimizer is kind of changing the shape, but also to some extent changing the twist of the aircraft wing, which impacts the pressure distribution. At the root and the tip, which are these two plots, it seems like the change is not that significant. But in the next slide, we show the pressure coefficient at these same stations. And you can see that the optimization diffuses this shock towards the trailing edge and pushes it towards the leading edge, but actually it's a much weaker shock than before, right? And here is the hypervolume plot, higher the better. So our algorithm is green. We also benchmarked it against other state-of-the-art algorithms. So notice that our method actually approaches the highest hypervolume much faster than other methods, right? So you can think of these iterations as function evaluations. So you want to arrive at the highest hypervolume with fewer iterations as possible, which is exactly what our function does. Okay, so to summarize, the method that we developed, qPOTS, is a fast, accurate, and derivative-free and sample-efficient multi-objective optimization method that improves on the state of the art. It has very strong empirical performance. We provide a lot of details in the paper. I'm going to give you a link to the paper. What I showed you is just like one experiment. And the NASA CRM experiment itself, after all the cleaning up and everything we had to do, it took 3 full days on about 300 cores on our supercomputers, right? So it's kind of a heavy-duty real-world optimization problem. We published our software on GitHub, so you can install it using PyPy, or you can just clone it, and feel free to take a look and reach out to us if you have any questions. All right, so takeaway is CSDL develops scalable computational techniques towards decision making for complex engineered systems, right? So we are more of those AI ML for decision making guys, which in a sense includes AI for science and AI for engineering. We primarily focus on method, algorithm, and software development on the decision making triads, so surrogate modeling, UQ, and optimization. And we predominantly work with probabilistic machine learning, which involves kernel methods with Bayesian decision theory. This is our website to our group. Feel free to visit that to follow what we've been working on. And I guess that's all I had. So here are some QR codes if anybody's interested in the AI stats paper and also the associated software. Yeah, that concludes my talk, and I'm happy to take any questions.
Yeah, thanks a lot. That was a pretty fun talk actually. Um, we can actually kick it off with some questions. So I had a few questions regarding both the DeepGP and some of the Thomson sampling related work.
Yeah.
So I think for the conventional GP, as you mentioned, when you're just dealing with stationary kernels, you could also like potentially look at your data and you could make some assumptions on what kind of kernel function you want to choose for it, depending on how you expect the length scale and other things to change. But is there any sort of guidelines from a practitioner's point of view or from a theoretical point of view on how to design the kernels for deep GPs? Because I imagine that maybe over there the behavior is not so easy to characterize if you just have, let's say, like meta kernels
Right.
going in different layers.
Right. So the whole point of deep GPs is that you don't have to design the kernel. You keep
Okay,
it as simple as you want it to, but you just increase the depth of the architecture.
I see.
So just add more layers, because every layer that you add, it essentially, what it does is each layer warps the input. So there's something called input warping that is very popular in machine learning, but particularly in Gaussian process literature, right? Um, you could have a really complicated function that you're trying to approximate using a Gaussian process, but if you transform the input to something else, right? It's also called manifold Gaussian process if anybody's interested. So if you do that transformation of that input to something else, then maybe the Gaussian process is able to learn that mapping a lot better than the original mapping, right? So the deep GP essentially does that input warping. So Z warps the input X before you fit a GP between Y and Z in this one layer deep GP. And then you can add the number of layers you want to increase the warping, which essentially increases the complexity or the flexibility in your expressiveness. So the idea again is to keep the kernels for these individual GPs simple, So in this case, we use a Mattern kernel, and the Mattern kernel with the differentiability parameter of, I think, 2 halves is equivalent to a squared exponential kernel. Don't quote me on this. I usually mix up 2 halves and 3 halves. But anyway, so we use a Mattern kernel, which is one of the simplest kernels you can use, which is sufficient for you to get a really sophisticated deep Gaussian process depending on how many layers you add.
Okay. And then I guess in practice, then you don't need more than 3 to 4 layers. Or I imagine that as you add more layers, you're also, uh, does it also then increase the cost of training it when you bring in the variational inference and all the other techniques?
Absolutely. We have never had to go beyond 2 or 3 layers.
Okay.
Um, and the general consensus from what we've seen is also, you don't need a deep GP. A shallow GP is sufficient. I mean, I'm not. Maybe there are examples. Maybe there are applications where you really need a very deep Gaussian process. We've just not encountered that.
Okay. Um, and then for the second question, so I think you mentioned that the Thomson sampling is related to the multi-armed bandit problem.
Yes.
So I'm just wondering about the connections between the multi-armed bandit and the GP. So is it the case that if you just take infinitely many arms and then make some assumptions about how the reward function is going to look like, you would essentially end up with the equivalent of what you do in GPs, where you are basically able to compute these posterior probabilities anywhere in the domain and draw these sample paths?
Exactly. So, so the extension of multi-arm bandit to optimizing a function, let's say this Ackley function, right, would be you have infinitely many bandits, right? And then in that case, so every X location, so I've not labeled it, but the horizontal axis is X. So every X location is essentially a bandit, and you have infinitely many of them. And then every X location has a certain probability of being a minimizer of this function, except you don't know what that is.
Mhm.
But you can learn that by making arbitrary evaluations here and there. And then once you learn exactly, which points are likely to be a minimizer and which points are not, then you can come up with a good approximation to that density, and then you can sample from that. I mean, I don't know. I feel I probably lost track of your original question.
Oh, yeah, I was basically just wondering if then some of the methods or like some of the other techniques from multi-armed bandits then also apply to the GP. So I think over there also they have or in sequential design with bandits, they try to apply methods where they update the preference function for each of the arms. And so then based on that, they decide like what actions to do next or where to sample next in the domain. So I was just a little curious
I
about
think
those
it's very
connections.
similar.
But I
Yes.
think, yeah, that answers it. Um, and one final question is related to slide 36, where you showed some of the maximum problem. Yeah, I was wondering if this is also related somewhat to the space filling design literature, because I think you do see like some, or at least in some versions of Latin hypercube design, they do try to frame it as this kind of problem, and then they also extend it to sliced LHDs where you try to acquire new points but ensure that the design is still satisfying like Latin hypercube. So is it sort of similar to that, or is this
Absolutely, it is. I mean, it is the same if you ask me.
okay?
The only difference is that we are somewhat lucky uh, in the sense that this X star, the capital X star over here, it's usually a discrete set because this X star is coming out of solving this cheap multi-objective optimization problem, right? And it's solved using genetic algorithm, which outputs a finite set of points. It doesn't give you like a functional form of the Pareto set. It gives you kind of a bunch of points. So it has finite cardinality. So let's say the cardinality of this uppercase X star is capital N. And then we are also searching over all the little n observation sites which is the capital X sub n, right? So solving this maximum problem is essentially computing a pairwise distance matrix, right? And this matrix is of size capital N times small n. So capital N is the cardinality of uppercase X star, small n is the cardinality of uppercase Xn. So when this n becomes, too big, then of course there is a problem, but there are ways to efficiently solve that. But yeah, I mean, to answer your question, it is definitely the same as, it is inspired from space filling design literature. But I just wanted to comment on, the difficulty in solving this because I didn't have the time to do that when I presented. Um, so in short, it's not that hard to solve this maximum problem for our problem.
Understood. Um, Other questions both in the room as well as online. Yeah, just
I guess like mostly this method's gradient free, right? And even in the traditional like MDR literature, like there are limitations of these methods. While you're using surrogates, like do you see any extension of this where you can leverage gradient information?
Yeah. I mean, in principle, yes, but I think um, the hypothesis behind everything that we develop is that we don't have access to gradients, right? Because if you think about, real world applications. So first of all, when you look at multidisciplinary problems, you have to compute the coupled derivatives that couples between two disciplines, right? And for that, you first have to have a very efficient way of computing the individual gradients. I mean, in the modern day, you could have automatic differentiation, but if you're using a legacy CFD code that was written in Fortran, then essentially you have to rewrite the whole code to accommodate automatic differentiation to compute those gradients. The alternative is to use adjoint methods, right? Adjoint methods are great in efficiently computing gradients, but in practice, they are very sensitive to changes in solver settings, mesh quality, and stuff like that, right? So we solve aerodynamic shape optimization problems where the mesh frequently changes, and even some subtle changes in the mesh can actually throw off the adjoint solver. So essentially, coming back to your question, derivative information is a lot harder than you think in practice. And even when it is available, it poses a lot of challenges, right? So the vision of our group is to develop methods that don't depend on derivatives and see how good we can do. And it turns out so far from whatever we've tested, we're able to compete well with gradient-based methods. Um, but if we have a situation where we do have access to gradients, then I think the I mean, I've never thought about it, but I think the first thing I would do is look at just gradient informed Gaussian processes, right? So essentially, you can condition your Gaussian process posterior on not just the observations, but also the gradients at all these observation sites. That just blows up the covariance matrix size, so that poses those challenges. But I think that's a seamless way of just incorporating gradients. But like I said, we don't envision doing that because of the challenges that I previously mentioned.
See. Like on a higher level, there seems to be like a two-step approximation. First, on a functional level, where you're just substituting your individual functions, f, I, g, p's, right?
Yeah.
So like the Pareto front, like the way you're approximating is there any way in this, like, I'm not sure if you showed this, but you can quantify the uncertainty in the Pareto front approximation as well, because inherently you're just making way too many approximations on a modeling level, right? The function level. So are there ways you can quantify the uncertainty in the output as well, like the Pareto front approximation?
Yeah, absolutely we can. But I think before that, I think I want to emphasize that the uncertainty in the Gaussian process approximation is a strength and not a weakness, right? So for instance, with just 20 points, so the 20 points are the brown circles that you see. So these are the points where we made observations to fit the Gaussian process. And using the Gaussian process surrogate model, the Pareto frontier that we predicted is the blue circles, which is clearly way off from the true Pareto frontier, right? But that's fine because we're not going to end here, right? I mean, if we had very limited budget and we had to stop at n equals 20, then you're absolutely right. We're going to have a really poor answer. But if this is just en route for you to finding the final answer, this is actually a strength because what it does is it tries to find, explore, and exploit the design space. So in this case, it finds a point here which tries to exploit its knowledge of the true Pareto set. And then at n equals 50, it explores. And then with more points, it again tries to exploit, right? Um, so the first answer is that the approximation error that we get due to the Gaussian process is not a problem in practice. In fact, it helps us to explore the design space. But if you actually delve into the theoretical aspects and say, hey, I want to uh, quantify the error in that approximation, then that error bound will look something like this, right? So right now, what we are saying in this theorem is that asymptotically, when n reaches infinity, the probability of the difference between the true function and your prediction through the Gaussian process will be less than some threshold epsilon with some probability 1 minus delta. And usually this delta is pretty small, right? And then this epsilon is also arbitrarily small, but the choice of this epsilon is going to determine exactly how many n's you would need to achieve this condition. But for finite n, you can actually compute this bound. And you can use that bound, and then you can kind of do some Cauchy-Schwarz type of games, and you can kind of come up with an error bound and exactly. I don't know what you would do with that, but if you care about quantifying the error in the approximation, you could easily do that.
I mean, like, can you saying the same theorem? So this talks about the approximation between the on the functional model level that you're approximating it by a GP. I'm saying like given finite budget, like can you like even for the identified estimated Pareto front, I guess, like can you also quantify the uncertainty in there?
Yeah, that's what I'm saying, right? So you begin by first quantifying. So you're saying uncertainty. I'm saying error. They're not the same, but they are somewhat related, right? So I'm saying you can put an error bound on whatever the Gaussian process model predicts compared to the true function, and then using that you can kind of go back and say what would be the error in the predicted Pareto frontier, for instance, right? In other words, I can come up with an error bound on these blue circles.
Right.
Okay, and those blue circles essentially would tell you how much approximation error you should expect, and then you can compare that against the true Pareto frontier, which is the black, crosses, and then say, if your error is acceptable or not.
Okay. All right. Thanks.
Hi. So this is a very interesting talk, and I look forward to reading more about your work. But in the meantime, in the initial part of the talk, we discussed like learning the underlying function space, like f of x given some input checks, right?
Yeah.
And you mentioned that so let us say we have, let's say, some 20 initial input conditions, and I can go and get more input data or more evaluate the function for more input data, but it will be costly. Or I can go increase the expressivity of the model by adding more layers to the Gaussian process. So do you have like an idea of how one would proceed, like choosing to get more data with the cost or like more expressive model? Like how one would choose between these two options?
Right. Good question. Yeah. So usually, people don't decide between whether you should use a regular Gaussian process or, I mean, I think one angle to your question is that you kind of keep the number of layers to your Gaussian process to be a variable, and then you try to find how many such layers are required. And if the number of hidden layers is zero, then you recover the regular Gaussian process. And if it's greater than zero, you have a deep Gaussian process, right? So that's somewhat of an architecture search for deep Gaussian process, which we've never done that. So in practice, we usually first decide if you want to use a regular GP or a deep GP, right? And usually deep GP is the exception. The rule is a regular GP. So we choose a deep GP if we have a reason to suspect that the underlying function has some non-stationary effects that we have to worry about.
Okay.
In which case we start, we first fix that we want to use deep GPs, and then we try to find maybe, how many layers would we need, and we don't do that rigorously. We just try 2, 3 hidden layers and then see which works best, and we stop there. But if you were to automate this process, then yeah, you have to do something called something like a neural architecture search, which automatically searches different architectures, which would include both regular GPs and deep GPs, based on some validation criterion, right?
Right.
In practice, though, even for, so I showed you a step function, right?
Sure.
The It's ideally for the step function, you would have to use a deep GP if you want to get a good approximation with limited data, right? But you can get a reasonably good approximation to the step function even with a regular GP, provided you have enough points, right? So sometimes, like I said, what people do is they kind of take a middle ground and they try to do some sort of an input warping. You might want to look up something called manifold GPs. They try to learn another function of the input space and try to fit the GP in terms of the transformed input space. And usually that gives a very good approximation to such functions, right? So yeah, I mean, like I said, there's no straightforward way of determining exactly, if you should increase the depth of your architecture or if you just need to sample more points. I think that heavily depends on the context, and more often, what we do is just fix a GP architecture and increase the number of training points.
I see. Okay, thank you. And one more follow-up question. So in this case, we have like one step function, in the inside the domain, and we see that like a two-layer GP is like good enough, right?
Yeah.
But is there like a correlation between like the number of non-stationary points in your system or in your domain of interest and the layer of GPU required, or like is like, do you have like some ideas about that? Or
Yeah, I don't think so. Let's say if you had like a hat, like a function that looked like a hat, right? So it kind of went through a step first and then came back down.
right?
There is no reason not to believe that the same two-layer deep GP would give a good approximation to that, right?
Oh, I see.
So in
Okay.
other words, just because you have multiple jumps, you don't need multiple layers, right?
Okay.
It's just like I said, the intermediate layer in a deep GP tries to warp the input
Mhm.
to the next GP such that the approximation is much better captured in the warp space. And
Mhm.
like I said, pretty much all the work we've done so far has used 2 or 3 layers at most.
Okay. Okay. Sounds good. Good. Thank you.
Okay. If there's no other questions, I think we can actually conclude the seminar here. Thanks again for this. Really nice talk. And yeah, I think we learned a lot from it.
Yeah, thank you so much. And yeah, feel free to reach out if you have any questions about our work. And yeah, hope to catch you guys in one of the conferences.
Yes. Thank you. Thank you.
Okay. Have a nice day.
Yeah.